recording? Okay, good.
Okay. Good morning, everyone. I will introduce myself. I'm Zhang from Sternberg. Currently, I'm a postdoc. And this is my title. My title is Experimental Signatures of Nuclear Structure in Heaven Clearance. And in this slide, I show the nuclear chat. Actually, this nuclear chat is studied in the low energy community, and they try to understand the nuclei and also the nuclear interactions inside of the nucleus. But in heaven clearance, we also collide the nuclei. So here we want to learn from each other and we want to benefit both. And this is my outline. First of all, I will introduce the nuclear structure and the heaven clearance. Next, I will show some results in the large clearance system at RIC and LC. And in the third part, I will show the isobar clearance at RIC, and I will give some future intervals and opportunities. And finally, I will show some concurrence and analogs. So actually, in the world, the lots of nuclei can have different shape. It's like they can have a rugby ball shape, like and also have a pear shape. And some nuclei can have a triaxial shape. And also people want to study the neutron skin, which is related to the symmetry energies. This plot shows the different distribution between proton and the neutrons. And in the light nuclei, and some light nuclei can have a clustering structure. In the heaven clearance, actually, we collide different nucleus. There's two very famous collider located in the USA at RIC, and also the CERN and large current LC. And at RIC, we have lots of clearance from large clean system, union to the very small asymmetric clearance, P-gold, D-gold, Henry-gold. And we also have a very large range clear energies from a few GeV to 200 GeV. And at LC, they also have P-lead, lead, xenon, and future the P-gold, P-oxygen and oxygen clearance. So this provides us a very good opportunity to study and to understand the nuclei. I will give a very short introduction since people already showed many times. And actually, two colliding beam within a speed of lights, and they can have a Lorentz contraction, and then they like a pancake here. And there's we can deposit energies, which is described by the kinetic QCD theory. And there's QGB droplet here. And after that, this QGB droplet can be described by the viscous hydrodynamics. And there's the hydronization, and there is finally this after interaction between the hadrons, these hadrons can be detected by the detector. So this heaven clearance is a multiple stage, and in experiment we analyze the final state particles using the soft and also the hard probes. Here I show some soft probes which is using the MPT and transverse flow. Actually, from the initial state to the final state, there is a very good linear relationship between the n part and the n charge, and also the MPT and size fluctuation, and transfer and entropy flow and eccentricity. This initial state can fluctuate. It has a eccentricity fluctuation. It also has a size fluctuation. But before that, we want to ask one question: can we image the nuclear structure by heaven clearance? This nucleons distribution is described by the deformed Wu size density, including lots of parameters. You can see here, there's quadrupole deformation, octopole deformation, triaxiality, neutron skin, and the nuclear size. So in the next few slides, I will show the result in uranium at RIC and xenon at LC. And I try to show you some promising results. Here, let's focus on the inject state firstly. And this plot is drawn by using global. And you can see if we input some bit values individually for epsilon n square, you can see epsilon 2 is mainly dominated by the beta 2, epsilon 3 is mainly dominated by the beta 3, and there's some contribution from beta 4, and epsilon 4 is mainly dominated in central is by the beta 4. If we add some 2 parameters input, you can see there's a little enhancement from another higher order beta n contributions. You can see beta 2. You can see epsilon 2 have two contributions from beta 2 and beta 3 in central regions, and epsilon 3 has beta 3 and beta 4 contributions. You can see this trend is largely enhanced. And beta 4 is most contributed by the epsilon 4 is most contributed by the beta 4. So we add 3 parameters: beta 2, beta 4, beta 3, beta 4, and you can see finally there's no very large enhancement. So in the previous study, we mainly focus on the beta 2 rule. In start preliminary, you can see the uranium. The V2 is enhanced. The gold is lower than uranium. This is mainly controlled by the quadrupole deformation in uranium clearance. And there's the empirical formula here. V2 is proportional to beta 2 square. V2 square is proportional to beta square. And in outer central region, we use a very famous multi-phase transport model. And in central regions, we can have a very linear relationship between the Wien square and the beta 2 square. But before we ignore the higher order beta 3 and the beta 4 contributions. This is the INT model. You can see if there's no beta 3 contributions, the uranium have a large mass number. So based on the fluctuation, the uranium should be V3 should be smaller. Indeed, the V3 uranium is lower than V3 go clearance. But in data, we see that the reversed behavior, the uranium V3 is larger than go clearance. So it means we should consider the higher order beta 3 components and also beta 4 components. And now we use the transport model to check this. And you can see this ratio is V2 ratio, V3 ratio, and V4 ratio between uranium, and the gold, between gold clearance and the uranium clearance. If we don't input any deformation contributions, you can see due to the size effect, the gold V2 is larger than uranium, and gold V3 is also larger than uranium, and the V4 is roughly equals to 1. If we input quadrupole deformation beta 2, you can see the uranium is the ratio is lower than 1. It means the uranium V2 is largely enhanced.
So exactly how does theta affect this? It just changes the shape of your source.
Yes, here we use deform Bosaks and change the shape of the nucleon distributions.
How much of the gold is incorporated is actually heated in your calculation? The whole thing.
Sorry.
I mean, when you have a collision,
Yes.
the matter is no longer ground state. So how much of the
Why not? I mean, after the collision, it's gone, right?
well, so you're measuring it after the collision, so right?
Yes.
So and then before it's cold, after you could say it's hot, you can choose what you want, but how much of the matter is heated by the collision? How strong is the overlap? And this?
Oh, yeah, that's a very good question. Actually, no. We always claim that in the out-center region, this the change of the deformation is 100% captured, but in the mid-central region there is a very different clearing configurations. So
I think your question is different. It's probably in the sense.
I'm trying to
there's
understand
no-
how the dynamics gets into the shape of
That's
your.
Right, because the crossing time is so short. 0.1 frame you will see. The dynamics, there's no time for the dynamics to set in, right? Means you cannot excite nucleus in, it takes much longer time to go from the ground state to excite state than 0.1 frame you will see. Means there's no time for the system.
Yes, but when you consider the decay,
Yes,
and you think that you are seeing a final state which is reflecting the geometry of the decay, but it's the geometry of the hot matter.
Yes,
decay.
That is true.
They're spectators. So the question I'm asking is, what's participant, what's spectator, what's configured, what's involved in this deformation? Because you're parameterizing the deformation, but that's for the entire nucleus. The question is, what is the deformation impact on the persistent region or the hot region? Colliding.
So the answer to your question is multiple. When you fix a certain multiplicity, you have a range of impact parameters, you have a range of relative orientations, and each collision has a different overlap. And the deformation of the nuclei and enters in some complicated way into the ensemble, but you see that it matters because it's not the same as if we were not.
What is the function for the deformation of fold?
yeah, here actually our deformation for good is minus 0.13, right? It's
Very small,
yeah, not large.
not very large. It's very large, very small.
So I will continue. Yeah. So if we input a very large beta 2 value, you can see the uranium V2 is largely enhanced. So that's why the ratio is less than 1. But for the V3, you can see the beta 2 value doesn't have much effect on the V3 ratios. For V4 ratios has some effect. That's why the ratio is even 1. That's because there's linear and nonlinear components from V2. So if we input beta 3, you can see there is a little difference between these. So it means that the beta 3 can contribute the V2, but for V3, the trend is totally reversed. So it means the V3 is mostly dominated by the beta 3. For V4, you still have some difference, some contributions. If we add beta 4, the trend doesn't change too much. It means V2 is not affected by the beta 4. And but with this V3 ratio, there's a concave shape. It means the beta 4 can have a concave shape, can give a concave shape combining with beta 3 for V3 ratios. So finally, if we observe this concave shape in the experiment, it means there is a beta 3 and beta 4 contributions. And this is V4 ratio. This is V4 ratio. So this ratio, after including the beta 4, you can see there's a large drop in the central regions.
What do you mean by N-charge scale?
Yeah, N-charge scale is this is the ratio. So we need to scale down uranium to the Google plate.
You know, it's the same as centrality, or
Roughly, it's same.
you rescale by the average number of N-charge, the mean bias.
We scale the value at knee values. The N-charge distribution at knee, so we just scale this.
Do you do the same analysis with lead? Do you see any of this?
Okay. You mean and lead as numerator or denominator?
Well, you're analyzing what you see. So
Yeah.
Your disagreement with theory, you're interpreting it versus beta. So if you did lead, you made all these beta values are 0. That's not as good a spherical nucleus as you can find. What do you see?
Oh yeah, that's
that's just a model.
Yes.
Right? So that would be the black, the first black line.
Oh, so you don't have data?
This is the only transport mode from MBT, and this, yeah, I need to mention that, sorry.
Okay.
And finally, I took some parameters on this the papers, and we see that there's a drop. The ratio is less than 1 between between gold and uranium 4v2, and there's a concave shape. You can see here in the central region. There's the ratio is less than 1 4v4. So we hope we can do this in the future experiment. Just make a ratio.
I have a question. So on your V3, there are lots of wiggles that are bigger than the size of the air bars. So is that?
I mean this one, right?
Yeah, stuff like that. Is that real? Or is that not?
Yeah, I use lots of things, so I remain in this behaviors.
Sorry, I'm a bit confused for your V4,
Yes.
because you have the red line, which just has beta 2, you have the purple line that just has beta 4, but then you have a green line that has a beta 2 and a beta 4, and that in fact goes back up to 1. So I would assume that, I mean, if you look at the way beta 2 and beta 4 are interacting, they keep bringing you down this ratio, but then why is the green line bringing you back up?
Yeah, you can see here. There's the red one is the beta 2, the purple one is beta 4. If we add the beta 2 and beta 4, so finally the green one is here. Roughly
The
here.
green one has a smaller beta 4.
Yeah,
That's
the
before.
beta 4 value is here. It's much smaller.
Oh, okay, the beta 2 is the fault, but the beta 4 is
Beta
not.
2 is very large.
But
for other
still,
sides.
it looks like it's kind of above the other, just beta 2, not beta 4.
Okay, look the formula there, right? This is the expected contribution. So if you, it's a quadratic dependent. So if you increase the beta value by factor 2, it's actually factor 4 by the impact of beta. So you really need to look at this formula to have a quantitative. It's kind of
And
quantitative.
that's, so I mean, it's above the one without any beta 4 at all.
Probably should do.
Yeah.
I'm sorry, that's a stupid question, but why do you do gold and gold over uranium rather than reverse?
Oh yeah, that's I want to show a very clear picture to you. That's why I reverse. But I can still
Okay.
do another ratios. That maybe that's a good way.
If uranium is one today, projects once it's put in the numerator, otherwise it's backwards. Flipping your chain gets smaller, the slot gets bigger.
Yeah, so as I mentioned before, on the size of Q drop, it can also have a size fluctuation. So if you give any distributions, you can calculate the mean, the variance, squamous, and closest. The very naive picture is for the fixed end part, the small size can have a large radial flow, large expansion. For the large size, at the given end part, it have a smaller expansion and the smaller MPT. So we calculate these distributions, and there's a pocket formula here. You can say the variance is proportional to beta 2 square, squamous is proportional to beta 2 in the third order, and also have a gamma dependence, and the closest has a negative beta 2 in the fourth order. So this calculation is from global calculation, and we check this in very interesting like pictures, and you can see if we input different beta 2 value, the variance of the size is enhanced. For the this happens also happen in the squamous, but for closest, for the normalized closest, if we input a very large beta 2 value, there is a sign change. So we can do this in the uranium clearance. So here is the data. You can see there is a good and uranium data shown at dot points, and there this is normalized variance, this is normalized squamous, this is normalized closest. So if we only focus on the data, you can see the uranium have a large values, and for the normalized variance and normalized. Oh yeah, okay. So there is a large enhancement, and this is due to the deformation, as I mentioned in the previous slides. And if there's no any deformation, this fluctuation is roughly has a number of source scanning. is 1 over n in the variance and 1 over square root n in the closest. And basically these pictures are captured by the deformation. And we also compare the hydro model, which is provided by the Bianchi and the Trinchen, and even because this hydro computation is very expensive, it's very high, so we need more statics in future. And here we can combine two pictures. We can use a wave flow, and we can use a MPT, and we can calculate the correlation between them. And this is an example for very poly nuclei. In the central region, you have body-body and tip-tip clearance. In the body-body clearance, the overlap region is large, so it means there's a smaller MPT, but the shape is more elliptic, so there's a large epsilon2. So we can have a anti-correlation between these two V and PT. But for the tip-tip clearance in the central region, so this overlap region is smaller. There's a much larger expansion. The mean PT is large, but this shape is more circular. So the epsilon2 is very small. So now I use Pearson correlation between V and the mean PT here, and the covariance in the numerator and also the variance in the denominators. And here you can see there's a dramatic sign change in the central region, and the trend is continually decreasing for uranium. For gold clearance, they are positive because gold is smaller deformed. It's an oblate shape. For Pearson V3, they are positive because V3 is mostly fluctuate driven. So they are expecting the positive signal. And we compare these calculations provided by Giordano, and they use a Tran tool, which assuming the way is proportional to epsilon and PT is proportional to energy over entropy, and they calculate different input, and you can see the hierarchical trend is captured in the Tran tool. The value is around 0.28 here. And we also compare the 4 hydro calculations here, and the hierarchical trend is still captured by the Tran tool, by the hydro calculations, and the values can also be constrained around 0.3 for uranium clearance. And in this slide, I showed some results from LC energies, and if Vina is have a beta 2 value, but these 3 axes are not equally to each other, and you can see there's a triaxial shape, and we use global and ABD to check this. So the Pearson have this pocket formula, gamma and beta 2 dependence, and this is also studied in the hydro calculations, and they compare to the R-class data, and you can see there is some triaxiality values for Vina clearance, and it's all for the lab for the V2 ratios. They confirm the Zina is in a poly shape, and the MIPA ratio in different media ranges in R-class data, and you can see even for different medium transport in different media ranges, the ratio is robust, and they compare different the gamma value input, and they can roughly constrain the Zenon shape at LC energies. And the most important things, we are also trying to understand the initial state, so we can compare different model calculations from different series. And actually, we have multiple ways to deposit energies, and this energy is related to the anisotropy flow and also the MPT. So the LC result from Atlas and Alice and the future CMS result, they give a novel way to characterize the initial state and also help us to understand the initial state. And the next slides, I will show the nuclear structure in the isobar clearance. Since these 2 isobar clearance have the same mass number but different proton numbers, and so usually they are used to study the Kerr-Mank effect. And finally, there's famous plots inside this paper. There's the ratio is not equals to 1, so we are trying to find what's the reason for this. And you can see if we connect some transition rate from low energy experiment, you can see the ruthenium is a little bit deformed, and the zirconium have a beta 3 maybe, but it's a larger range. So we make a final bin in the V2 ratio between ruthenium and the zirconium, and you can see there's non-magnetic trend here. There's a bump in the mid-central and increase in the central region for V2 ratio. For V3 ratio, the ratio is continuously decreasing, and this behavior is captured by the deformation in the neutron skin. In the most central regions, V2 ratio is most dominated by the beta 2 and beta 3, and the V3 ratio is dominated by the beta 3. So that's why if we meet the ratio, we can see there is an increasing in the central region and a decrease in the V3 ratio. But the neutron skin can enhance the ratio. That's because at fixed imperial parameter, if the nucleus have a neutron skin, there is a more smeared, so the epsilon 2 is smaller than the other nucleus without the large neutron skin. So we also calculate the mean beta fluctuation in the isobar ratios. There's a drop, there's concave shape here, and this is mostly dominated by the nuclear deformation between ruthenium and zirconium. And also there's indication of quadrupole deformation and octuple deformation in these two nuclei. And this is a new in-charge distributions, and you already talked many times. And there's bump here. This bump is more dominated by the neutron skin, and that's because the neutron skin can control, especially in the mid-central, can control the NMBB clearance, also the particle productions. For the central region, we found there's some a little bit different. There's deformation can affect a little bit the in-charge distributions. So Haoji also studied this, and they find another important promising way to study the neutron skin to constrain the L parameter, the slope of the signature energy at the saturation ρ0 region location, and their constraint is roughly equal to the empirical calculations from lots of groups, and they try to constrain the signature energy and the L values from the heavy ion collider. And another way is we can use ultra-peripheral clearance to detect a neutron skin and to constrain neutron skin. I think Zhang will give this in details. And in this slide, I show lots of non-magnetic trend between ruthenium and zirconium. It means in heavy ion clearance, the nuclear structure can affect the soft probes in multiple ways. So that's why I think it's good to study this, understand in the high clearance. In the future intervals and the opportunities, as we there's an indication between of the octuple and the hextuple in uranium clearance, and it will be good if we complement this using the star uranium clearance. And for the light nuclei, the RIC already took a very enough data, and also with EPD4 detector and in the oxygen oxygen clearance. So it's good. It's good opportunity to study the cluster in the RIC and also the future LHC P oxygen and the oxygen clearance. And we're also on the way to try to understand the initial state. So here's my concurrent looks. I think. Thank you.
Question?
Okay, if you go back to slide 11, so just for a little bit of clarification. I think Juliano also showed a little bit study on this in his talk on Monday, but what we see, I mean, the reason we actually making this reverse ratio, I think motivation is that we want to understand the reverse ordering of the V3, because naively you think a smaller system always have larger flow if it's all fluctuation, because the fluctuation is like scales like 1/8 mass number. The less nuclei you have, the larger is your flow, because the fluctuation give you larger eccentricity, right? But then the data shows the reverse ordering for the V3. Means the V3 uranium is 20% heavier, but it actually have a larger V3. Right? V3 have a naively you immediately think, okay, I'll come into Giuliano, his talk. Right? Let me introduce a beta 3 in the uranium that will be responsible for that enhancement. Okay. But the point is that go to that this plot is that go to 11, slide 11, is that in fact you should not only consider beta 3 because the beta 4 can also do the same, but they impact in different region. So I think the point is that you really need to think about simultaneous constraint of this beta 2, beta 3, beta 4. You cannot just look at one observable, right? I mean, the looking at this, what you could do is that you measure the V4 ratio. If the V4 ratio is only have an impact from beta 4, you can just look at the ultra central region. Use the data you sort of know, okay, beta 4 is small or beta 4 is large, right? And then once you constrain the beta 4, then you can move on to the V3 because V3 only are influenced by beta 3 and beta 4. Now beta 4 is constrained. Let's look at the role of the beta 3. Once beta 3 is constrained, then you can go back to V2 because in V2 case, only the beta 2 and beta 3 contributes, right? So you cannot just look at one observable, especially for this very deformed species. There could be multiple shapes. But I think for isobar is simpler, but for uranium, you need to look at the multiple observables, systematically see if you can simultaneously describe all the ratios. I mean, we may need to reverse the ratio, but this is a little bit complex story. I think we try to convey to you. Okay.
Wait.
Yeah, wondering whether you can look at like V24 to V22 ratio. So whether that's sensitive to the deformation, because that should be good in canceling the penalty effect.
Yeah, you mean the V24, V22 ratio between gold and uranium?
No, just within one species. I mean, if the goal of taking the ratio between different isomers to cancel the penalty effect.
Yes,
then
yes.
you should be able to achieve that by just taking the V24 to V22 ratio within one.
Yeah, yeah. We did this in the isobar, but somehow we didn't do this in the uranium.
Jackie?
Yeah, I guess just to follow up on May's question, I would really like to see that, especially with for V4, because I suspect that what might be happening with those two lines being so similar is some of that's going to fluctuations and not the overall ratio.
The production is independent.
Yeah.
It's the case for 19 or something. For understood.
Unfortunate. Any questions? It's good.
So maybe I'm not fully understanding, like these data that you considered here, you kind of take these are static deformation. But in this collision process, you can observe dynamic effects. And what you see is maybe a mixture of both. How do you disentangle, or aren't you sort of making some extreme assumptions just by assuming that everything that you see just comes from static?
Yeah, actually, when I did in the low energy series, I think these values are from the static nuclear deformation, right? But even the high energy is a complex dynamical process, but this static nuclear deformation is still static. I don't think it will transfer to the dynamical deformation.
From the very few studies that have been done, I think they have limited sensitivity to fluctuations in the shape. I mean,
but this is a uranium. I mean, according to the nuclear structure, they are rigid rotor, right? But indeed, I mean, actually, I might going to show a talk where he actually studied the fluctuation explicitly, and you will see for two particle correlation really doesn't matter.
yeah, you can really understand this is some sort of average.
Yeah, I mean,
This is actually this average V2 square proportional to average the beta 3 square. I need to add that.
you forgot that.
I didn't forget, but I already sent to the secretary by email.
Oh,
That's sort of a random question. So beta 2, beta 3, and beta 4 here in most simulations are always aligned exactly with each other. Does this matter? If you included other components or allowed them to have different
well, the
orientations?
particle doesn't matter. I mean, global model have demonstrated that different internal degree freedom, like you have these different projections, right? The beta two have a triaxiality, for example, it doesn't matter for two particle correlation. Because in order to see let's see, beta three have 7 different projections, right? In order to see this internal degree of freedom, you need to go to 3 particle correlation. 2 particle doesn't care.
So making them correlated a lot more than they might be, doesn't matter.
It doesn't
The fact that
matter.
beta two and beta three are correlated with each
I
other.
think global model study have demonstrated doesn't need it.
Okay. Other questions? Anything remotely? If not, then thank you again.
Thank you.
And let's go to lunch. Right?
There will-
No.